With that we come to the end of the derivation part, numerical aperture and acceptance angle and all that. So now we'll be looking at factors that affect optical signal integrity. So before we go into that, this quick point which I want to draw your attention to, just a minute guys. Okay, so yeah, we'll look at factors that affect signal integrity, but before that, what does this sentence say? To launch light into the fiber, you need to match the spot size of the focused beam and the numerical aperture of the lens. So numerical aperture, we just saw it. It is the maximum angle at which you can shine light so that you don't lose anything. So that part of the sentence, what it's saying essentially is that when you launch light, you should make sure your incidence angle is less than or equal to the acceptance angle. Otherwise, you're going to lose some signal. So that part is somewhat clear. We looked at it already. Now, what do they mean by spot size of the focused beam? So the thing is, your cladding or core, your entire optical fiber is going to be a very thin cylinder. It's not as big as your normal PVC pipes and all. So if you look at one of the earlier slides, your entire diameter of the core is from 8 microns to 62.5 microns, which is a microscopic size. And the normal laser light, your pen lights and kind of things you get, they are of the order at least millimeters. So you need to make sure that your beam of light which you are shining is narrow enough to pass entirely through the core, because if your light beam is wider than the core, you are going to lose some information. So that's what they mean by spot size. So with that out of the way, we'll move to factors that affect optical signal integrity. So what do we mean by optical signal integrity is that you want the signal you send at your starting point to reach your destination without any sort of loss. But ideally that is what should happen, but sometimes in real scenarios there are various factors which lead to some loss of signal. So what are those factors is what we are going to be looking at. There are two major such factors, attenuation and dispersion. So what are these attenuation and dispersion? Attenuation is the reduction in the amplitude of signal. So how I like to explain this is, you take a rubber ball, some tennis ball, cricket ball, something, you throw it on the floor, it will start bouncing, but with every time it hits the floor and jumps back up, the maximum height it reaches is going to be less and less, like you see in this diagram here. The first time it will go to a really great height, the second time also more or less a good enough height, but slowly the height starts reducing and then after a point it just stays on the floor, right? Why does this happen? Because the ball is dealing with gravity, it is dealing with air resistance and all of those forces which consume the kinetic energy of the ball, which is why it cannot rise up to the same height every time. The height eventually starts decreasing and after a point it becomes null. So that is precisely what your attenuation also is. It is the reduction in the amplitude. So generally when you send out a wave, you have a specific amplitude, it will keep going, but due to certain factors, and what are these factors we will see later. So because of these factors the amplitude keeps decreasing, and because of this loss of amplitude you have a possibility of losing some valuable information. This is called attenuation. And the second is dispersion, increase in pulse width. So in simple terms, what is dispersion is, you have a normal wave like this. This is its time period. This is the time it takes to complete one cycle. This is its time period. But as your wave progresses through longer distances, it becomes wider, meaning the time period increases. From this point, your initial time period was this, now it has become this much, meaning the wave is basically slowing down. It's taking more time than it expected. That is called dispersion.